We needed to know composition of functions in order to find inverse functions. Okay, then you could ask me, what's an inverse function? Have we talked about inverse functions before? Have we done anything with inverse functions? Yes, we have. For example, these two are inverses of each other. These two are inverses of each other. And then we're going to learn a whole new realm of inverse functions that deal with what are called exponentials and logarithmic equations. Notations of inverse functions. How do we know if a function is going to be an inverse or not? We use the -1 exponent to represent the inverse. Remember, mathematics is a universal language. Anywhere in the world, you put that symbol, they know if a person knows mathematics, they can communicate with it. So if we put these two together, if we did a composite function with these two, what would happen? What would it end up with? Yeah. If we did f of g of x, and we put this one inside there, it would equal what? X. If we put this one inside of there, it would equal X. Same with this one. So what we're looking at here is this is going to be one of our tests. And also, because of that, it has to work both ways. So if you think you have an inverse function, do a composite function with it and see what happens. If everything cancels, you're just left with an X, then you have it is a true inverse function. To find an inverse, the procedure is very easy. Remember how we found the x-intercepts and y-intercepts? How do we find the x-intercept? And then do what? Solve for x. How do we find the y-intercept? Same thing. Set x equals 0, solve for y. Inverses are pretty much the same thing. To find the inverse, first thing you do, switch x and y. And then from there, solve for y. That y has now become your inverse. And we'll do some of those in a second. So let's look at example 1. G is an element consisting of these components. of these points. So tell me what G inverse would be. I know we haven't talked about this, but any function, when you plot the points of a graph, how many points are there? Infinite number of points. These little squiggles, they represent a set. A function is a specific set of numbers that define that graph of that function. So this is just a small number. So my inverse is also going to be a set. What's going to be its first point? Y. Because we switched x and y, it becomes 4, comma 2. We switch x and y. The next point is 3, comma negative 1, and then 0, comma negative 2. So that's how we look at the graphs of points of inverse functions. Basically, an inverse function is a reflection about the line y equals x. Think about it. If I had the point 2, 4, if I had the point 2, 4, what's its inverse? It's at 4, 2. It's a reflection about the line y equals x. Even if you think of that, remember I told you x squared and square root of x are inverses of each other. What function is that? X squared. This is square root of x. This is the line y equals x. Both of these points are on that line. So it's symmetric about that line. You know, it works the same for the cubic function. Okay. Now let's find if I give you y equals x squared, so x plus 5. Let's do that one first. Find the inverse. So your first step is switch x and y. So we have x is equal to y plus 5. That's our first step. Now we solve for y. So we have x minus 5 is equal to y, which is equal to our inverse. So our inverse is x minus 5. So how would you test it? Yeah, we'll do, so this is y1, this is y2, so we'll do y and inverse of y. So we have y inverse of y of x. So we take this function, the inverse, plug it into x of the original function. So we have x minus 5 plus 5. The 5's cancel, we're left with x. Check. That's what we're supposed to have. Then we check the other direction. Y inverse of y of x. So now we take this equation and plug it in place of x in that equation, which gives us x plus 5 minus 5. The 5's cancel, which leaves x. Check. So y x plus 5 and y inverse equals x minus 5 are inverses. Any questions so far? Now, what this is telling us, there's a unique property if a function has an inverse about it. Well, we haven't talked about the first one, which we were going to do originally, for example, 2. Remember, the original equation for example 2 was this one. Find the inverse of that function. Okay, I love it that you all are trying to work it out. No solution. This one does not have an inverse. Why? Because it has to do with the domain of a function of itself. Because if you switch x and y, there's no way you can get y by itself. Now, that leads us to our next discussion. So there's no inverse. Well, actually, let me get that. There's no inverse yet, because remember I told you earlier that the inverse of x squared is the square root of x? As long as we're at the origin, it's symmetric about the origin, we can have an inverse of it. But this one has been shifted. It's no longer, it's now shifted down and to the right. In order, in order for a function, where did that come from? Oh. For a function to have an inverse, it must be 1-to-1. One-to-one functions. A function f of x is, instead of 1-to-1, I'm just gonna write that. It's the same thing. A function is 1-to-1 if different inputs produce different outputs. Meaning, if A does not equal B, then f of A does not equal f of B. And if A equals B, then f of A equals f of B. So that's what it means. So if the inputs are the same, the outputs have to be the same. If the inputs are different, then the outputs are different. That's how two functions are 1-to-1. They're identical functions. So we have 1-to-1 functions and inverses. If a function f of x is 1-to-1, then its inverse f is a function. What does that mean? How do we know if it's a function? Remember that rule? What rule do we use to define a function? How do we test it? No, the vertical line test. Remember, in order to be a function, if you draw a vertical line on the graph anywhere, it only touches once, which is exactly what you said. For every one x, there's one and only one y. So it has to be a function. So if the function f of x is a function and it's 1-to-1, which means for every one x there's one y, then its inverse is also a function, which means for every x there's only one y. Why is that? Because remember, we just switch them for the inverse. Number two. The domain of a one-to-one function is the range of the inverse of that function. Why is that? Let's look at that. Why is that? The domain of a one-to-one function, one-to-one function f of x, is the range of the inverse. Because we switch x and y. Because we switch x and y. Remember, x and y are the domain and the range of a function. If we switch x and y, we switch the domain and range. Conversely, the range of a one-to-one function f of x is the domain of its inverse. Everything switches. If a function f of x is increasing on the entire domain, then its inverse is decreasing on the entire domain of its function. If it's one-to-one, think about why is that? Think of all the points that are increasing. If you switch the points, remember, you flip it across the y equals x axis, it's now going to be a decreasing function. This will be apparent when we start talking about exponential functions. Let's look at an example. Okay, given f of x is equal to 2x minus 3, prove f of x is a one-to-one function. With what we just talked about, how would you prove that a function is one-to-one? That it has an inverse. If it has an inverse, then it's one-to-one. So we have y equals 2x minus 3. Switch x and y and solve for y. And then divide by 2. So y inverse is equal to x plus 3 over 2. That doesn't prove anything to us yet. We have to test to see if it's a true inverse. So we take our inverse function, anywhere we see an x in our original function, plug it in there. So we have 2 times x, which is x plus 3 over 2 minus 3. So the first thing we got to do is simplify. Before you multiply fractions, can anything cancel? Yes, the 2's cancel, which gives us x plus 3 minus 3. The 3's cancel, which leaves us x. And as you can guess, if it works one way, it's going to work 99% of the time with the other way. But let's just test it. So take the original function, anywhere see an x in the inverse, plug it in there. So it's 2x minus 3 plus 3 over 2. The 3's cancel. 2x over 2, the 2's cancel. So yes, that's an inverse. It's an inverse of y. So y is 1 to 1. Since the y inverse is the inverse of the original function, that means the original function is 1 to 1. Example 4. Given the function x squared, prove g of x is not 1 to 1. And then I'll clarify what this means and why it works in a second. So we have y is equal to x squared. X equals y squared. Solve for y. When you solve for y, what do? You take the square root of both sides. When you take the square root of something squared, what do you have to do to the answer? It's a plus or minus. So my inverse is no longer 1 to 1. It's now 2 to 1. But they are still inverses of each other because we just proved it earlier. If we take the square root of x and put it inside of x squared, we get x. If we put x squared inside, that's called restricting the domain. If a function is not 1 to 1 because of its domain, we can restrict the domain. In other words, we're not going to take any negatives. So we're only going to look at the first quadrant for x being greater than 0. Now it's going to work. The reason it won't work because x squared looks like this over the entire domain. If we flip it across the line y equals 1, it would look like this. That's not a function anymore because it violates the vertical line test. That's why if we restrict the domain, if we don't look at any negatives, now it's a one-to-one. It's an inverse. So if you have a function and one of them is one-to-one and the other one isn't because of some algebraic manipulation, we can restrict the domain. We talked about all those already. G of x is equal to x cubed plus 2. We have 3 questions here. Is g of x 1-to-1? If so, find its inverse. And then graph them. So is A yes or no? How do we know that? No. You said yes. It has. You can't imagine. Mathematics doesn't work with imagine. Mathematics works on numbers or proofs. So you said yes. Why? Okay. If there's no proof, there's no answer. So the first step we do is switch x and y. Now what? Now solve for y. Then here we do what? Take the cube root of both sides. Do I have to put a plus or minus in front of the answer? Why not? Because it's a cubic function, which is symmetric about the origin. So the inverse exists Is it a function? What's the graph of it look like? In order to be a function, its graph has to be one-to-one as well. What's the graph of a cube root function look like? That's the cube function.
Oh, yeah.
Uh,
Oh, yeah.
The cube function is that. The cubic function looks like this. And you see that's a function because it passes the vertical line test, which is also why we don't need a plus or minus in front of it. So it is one-to-one, check. I found it. We graph them. X cubed plus 2. What's that going to look like? What does x cubed plus 2 look like? Cubic function shifted up 2 spaces. So here's my new origin for it. So it looks like this. What does its inverse look like? The cube root of x minus 2. Shift it to the right 2 spaces, and it's going to cross there. So it looks like this. And what we notice is where they intersect is going to be on the line y equals x. Again, if the graph was normal looking, it would be perfectly symmetrical. In other words, if I took my page and folded it across that line, it would be exactly the same picture. All right, any questions? That's the end of that section.